The World Wide Web is an ever-expanding graph of tens of billions of interconnected nodes. But to understand how information is retrieved from this network, we have to push past the macrostructure and look at an HTML document. There is a persistent misconception about how search engines operate. When you type a query into a search bar, the engine does not reach out and scan the live internet to find your answer. Scanning billions of live web pages on demand would take days. Instead, achieving millisecond latency requires the entire web to be downloaded, parsed, and compressed into a static back-end data structure long before you ever press search. Building this architecture requires solving three specific engineering problems: discovery, to systematically find the data; structuring, to organize text for retrieval; and ranking, determining which documents matter. These three pipelines run continuously and asynchronously in the background. They are completely decoupled from the user-facing search interface. This distributed backend is the machine that ingests the chaotic, decentralized web and outputs a highly optimized mathematical index. The ingestion pipeline begins with the crawler loop. This process starts at the URL frontier, a massive priority queue seeded with high-quality starting links. If a crawler operates without constraints, fetching pages as fast as its bandwidth allows, it will overwhelm target servers and effectively execute a distributed denial of service attack. To maintain domain politeness, the URL frontier groups incoming requests into isolated domain buckets. Rate limiters apply a strict time delay between outgoing requests to the same domain. The crawler verifies permission, fetches the HTML, and extracts new links to feed back. Beyond rate limits, the crawler must actively detect anomalies like infinite loops or dynamically generated calendars, where a server produces endless distinct URLs that trap the ingestion cycle. Without strict queue management, deep deduplication, and enforced delays, a web crawler behaves like a professional data collector rather than a malicious botnet. As the crawler extracts billions of new links, it has to answer a single question: have we seen this URL before? Running that check against a standard relational database for a 2 billion record dataset introduces crippling latency. Storing the full URL strings in RAM to speed up lookups requires hundreds of gigabytes of expensive memory, making exact matching inefficient at scale. To solve this, a Bloom filter passes the URL through multiple hash functions, mapping it to a binary array. If all hashes hit ones, it's likely a duplicate. If any hit a zero, it's new. Rare false positives are handled by secondary database checks. Massive scale architecture frequently relies on probabilistic data structures like this, systematically trading perfect accuracy for O of 1 speed. The raw HTML fetched by the crawler is not searchable. It is a messy combination of tags, scripts, and unstructured text that must pass through a strict lexical parsing pipeline. First, text is tokenized. Common stop words are dropped. Remaining words undergo stemming, down to a root token, run. This diagram shows the inverted index, mapping parsed terms to integer arrays. Those integers are document IDs, forming a posting list, a sorted sequence of every document containing that exact term. Constructing this index for petabytes of text on a single machine is physically impossible. Memory and compute limits would be exhausted almost immediately. To build the index across thousands of machines simultaneously, search engines rely on a distributed processing framework known as MapReduce. In the mapper phase, parallel worker nodes parse their chunks of the web, extracting words and emitting key value pairs associating a term with its document ID. During the reducer phase, the framework groups these identical terms across the network. It aggregates and sorts the document IDs, compressing them into final posting lists. The inverted index completely reorders the web's data, discarding individual pages as the primary container. Instead, it organizes data by vocabulary, allowing instantaneous set intersection for any combination of words. But an inverted index only provides retrieval, not relevance. A query for Apple intersects millions of document IDs. The system must sort those hits. Pure lexical frequency, how many times a word appears on a page, is easily manipulated. True relevance requires evaluating the topological structure of the web itself. This basic web graph represents PageRank. A page's authority is determined recursively by the quantity and quality of incoming links. This topological graph translates directly into a transition matrix, where every column represents the exact probability of a surfer clicking an outbound link. PageRank captures human endorsements, encoded as hyperlinks, and aggregates them into a highly computable structural matrix. The core premise of PageRank is that the final authority score of every page is exactly equal to the principal eigenvector of this transition matrix. However, the raw web graph contains anomalies, like spider traps, clusters of nodes with no outbound links. In a pure Markov chain, these dead ends absorb all probability, preventing the matrix from converging. The solution is a mathematical escape route, the damping factor, beta. It introduces a teleportation probability, simulating a surfer jumping to a random URL. Combining the transition matrix with this factor produces the finalized Google matrix. Calculating the principal eigenvector for a matrix with billions of columns cannot be done analytically. It is executed iteratively via MapReduce power iteration, continuously multiplying vectors until the difference falls below a strict threshold. Through applied linear algebra, the subjective web of links is condensed into a single deterministic ranking vector. Once the inverted index is built and the PageRank vector is calculated, the data is finally ready to be queried. But an index of this magnitude is too massive to fit into the memory of any single server. To solve this, the data undergoes document partitioning. The index is sharded across a global cluster of machines, typically routed by applying a modulo hash to the document IDs. When a query actually occurs, it triggers a scatter-gather topology. A central coordinator node receives the request and broadcasts the user's search out to dozens of shard nodes in parallel. Each independent shard performs a highly localized intersection of its specific posting lists, applies the pre-computed PageRank scores, and identifies its own highest ranking matches. Those shards immediately return their local top K document lists back to the coordinator node. The coordinator executes a final merge, re-ranks the combined lists, and returns the result. By strictly decoupling the asynchronous heavy lifting, the web crawling, the lexical parsing, and the eigenvector math from this real-time scatter-gather retrieval, the architecture achieves a constant time lookup. It provides results from across the entire indexed corpus in under 200 milliseconds.